सर आगे వచ్చేది इशू चार्ज
Hello, good morning, students. Hello. 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 Santosh sir. Audio is clear. Hello. Hello, good morning, everyone. Good morning, students. నవీన్ వినిపించిందా? Good morning, students.
మీకు చెప్పిన కొంత చెప్తారు ప్లేయర్స్ వినిపిస్తున్నారు స్టార్ట్ చేసేమాట.
Good morning, students. Now we have Dr. Abhishek Jasar with us. Today, Sir is going to enlighten us on the concept of robotics kinematics. Before that one, I want to tell few words about Dr. Abhishek Sir. Dr. Abhishek Sir is graduated in mechanical engineering and MTech in design engineering and PhD work related to robotics. He is concerned with robotics and flexible manufacturing systems. He completed his PhD degree from Department of Mechanical Engineering, Visvesvaraya National Institute of Technology, Nagpur. He got Hello, good morning. Hello. Hello, good morning. Hello. Hello, good morning to everyone. Hello, good morning. Abhishek sir, now it is audible, sir. Good morning, sir. Good morning, Abhishek, sir. Hello. Hello. Abhishek, sir, you can hear my voice.
Yes, sir. Now I can hear.
It is clear,
I
sir.
can hear, sir.
Okay,
Yes,
thank you,
sir.
sir.
And what about
Dear
mine?
students, good morning to all of you. Today, Dr. Abhishek Jha sir is with us. I want to spell few words about Dr. Abhishek Jha sir. Sir is graduated in BTech from Mechanical Engineering, MTech in Design Engineering, and a PhD from Viswesvaraya National Institute of Technology, Nagpur. His area of specialization is robotics. Sir has secured many awards and honors. One is PhD Scholar Fellowship by Minister of Human Resources Development, Government of India, and first prize in International Conference of Robotics Society of India related to advances in robotics, which was held at IIT Delhi during 2017. Sir has good skills related to the computational tools, MATLAB, MAPL, and modeling software, Robot Studio, Scorebase, RoboCell, Autodesk, Inventor, like that. Star has good publications. All the publications and patents are in the field of robotics. He filed three patents and three book chapters, and good publications in SCA journals, and he published papers in reputed journals also, and he presented papers in international conferences, altogether around 20 articles, and he is resource speaker for Atal program, that is AACT Training and Learning Academy online program. Two programs he addressed as guest speaker related to Atal, and at Viswesvaraya National Institute of Technology, Nagpur, he is the guest speaker for two programs, and he organized 8 workshops, which is a good work, which is commendable and appreciable. And he has good professional memberships. One is at Indian Society of Technical Education. Second one, Association of Missions and Mechanisms. Third one, Robotics Society of India. And he taught many courses related to robotics itself. Few of them are industrial robotics, mobile robotics, field and service robotics, medical robotics, artificial intelligence, and machine learning. Today, we are so happy to have Abhishek Jha sir with us, because very few experts are available in our country related to robotics. Sir is one among them. Welcome, sir, Abhishek Jha sir. Before commencing our lecture, I want to tell few words about our institution. Learning Institute of Technology is a premier institute established in 2008 by the Divine Body of Sai Dham Educational Trust of Visakhapatnam, with the blessings of Shirdi Sai Baba, to cater the needs of young graduates of in technology. Ours is autonomous college, which is spread in all directions with strength of over 2,600 students, over 200 faculty. The college is accredited by NAC with A grade and by NBA with 4 branches. And teachers are skilled and experienced, and they are committed to teaching. Related to the branch of mechanical engineering, we started a journey in year 2012. In a short period of 6 years, the department is accredited by NBA. And we got renewal also recently in the month of May up to 2015 June. We have extension of the NBA accreditation. The department has well-equipped laboratories and infrastructural facilities. The department boasts of high-end simulation laboratory, CNC laboratory, and recently R&D laboratory was commenced with good equipment to carry out the research work. This is about a brief introduction about our department, sir. Welcome, sir, and thank you very much for accepting our invitation. And our students are very much interested to get your advice, sir. Please start your lecture.
Hello? Sir, am I?
Now it is okay, sir. You start, sir. Now you restart it, sir.
Yes, sir. Sir, please make me co-host.
So you're
I'm not
already,
able to share my screen.
you're already a co-host, sir.
Please make it one more. My connection was interrupted in between. I hope it is visible to all. I hope my screen is visible.
No, sir, yes, screen is not visible.
Now is it visible, sir?
Not yet, sir.
Now is it? Is it now?
Sir, the connection is very slow, I think, sir. It's still not visible. It's showing it as Abhishek is starting to share content and the screen is blank.
I've already started sharing the content. So that little bit.
Sir, now we can see the slides, sir.
Okay, and please let me know whether slides are changing.
So,
Is it changing, sir?
not yet, sir.
It has stuck to the first slide.
Yes, sir. So maybe you can turn off your video and start sharing so that maybe the bandwidth would support that.
I hope now it's visible, isn't it?
Yes, sir, it's visible. The first slide, sir.
And is it changing?
Yes, it's changing, sir. Now it's on. Yeah, we can-
Thank you, sir.
Yes, sir. Thank you very much.
Thank you, sir, for your help. Okay, so once again, thank you very much, Sridhar sir, for giving me this opportunity to interact with you. And thank you very much for your kind words. It's my pleasure to interact with the students of your premier institution. So without wasting much time, I'll directly start my presentation. So the title for this topic or for this talk is about Introduction to Robot Kinematics. So this is the outline what we'll be discussing in this lecture. First, we'll see about the robots, then robot kinematics. Then, if the time permits, I'll try like to discuss a very good tool called Robo Analyzer. So to start with, what are the robots? Okay, so the first perception of robots come to the general people or general public from the movies what we have seen. Okay, so this is what was our first introduction or first insights into the robot through movies. Okay, so I hope all the students might recognize these robotic creatures, like this is the Terminator, Transformer, and this is the God of Robots, our Indian Chitti, then Iron Man. Okay, so these are the fascinating things what we have seen in the movies. So this is the perception of a general public or non-technical people about the robots. Okay, but if we come into the reality, these are the things. If we come into the reality, if we see the actual robots, these are the robots what we have. So they are far away from our imagination. They are far away from our imagination. So the first line simply denotes the serial robots or industrial robots which are being used in the industry, and the second category denotes the humanoid robots or the collaborative robots or mobile robots which are mobile in nature, they can move. These are the fixed base robots, and these are the mobile robots what we can see. Okay, and I hope you guys can identify this humanoid. Okay, so this is Sophia. So this robot, humanoid robot Sophia, has been given the citizenship of UAE. So now a date or till date, it is the most intelligent exists in our planet, Sophia. Okay, so if you see that these are the fictional things what we have seen, and in reality we have different machines. In reality we have different sort of robots. So if we try to define robots, what actually robots are, so simply we can say it is an intelligent system that interacts with the physical environment through sensors and effectors. But nowadays there is a very much buzz in the word intelligence, artificial intelligence. Okay, so therefore in nowadays you can use this kind of definition like intelligent system. Whenever we say intelligent system, it should have some sort of intelligence in it. It should have some sense of intelligence in it. Okay, but that is a different context. But in general, we can take the robot as intelligent system that interacts with the physical environment through effectors and sensors. So there will be certain end effectors, like here we can fix a tool, and for this humanoid robot, his hands are the end effectors. Here in the mobile robot, what we have again a manipulator and a gripper as the end effector. Okay, and these systems are equipped with a variety of sensors. These systems are equipped with a variety of sensors. So through sensors, these systems get the information about the environment, as well as those sensors are also necessary to get the internal state details of these robots or these devices. Okay, formally, if we look at the definition of the robot, then there are so many organizations like British Association, Japanese associations, ISO, Robotics Institute of America. So all these associations define robots as per their applicable norms. But if you compare those definitions given by the robots, you will have two common keywords in all definitions. You'll have two common keywords in all definitions. First one is reprogrammability, and second one is the multifunctionality. What we mean by the term reprogrammability is that we can reprogram the robot and we can achieve multifunctional tasks from it. Okay, so robots are reprogrammable as well as multifunctional. These are two keywords which define the robot. Okay, next, if we go for the classification, Well, if we go for the classification, then in general we can categorize robots into two categories. First one is the industrial robot, and second one is the field and service robots. Whenever we go for the industrial robots, again the industrial robots can be further subdivided into the two categories. First one is the fixed base robot, and second one is the mobile robot. This is the most general classification. And when we talk about the field and service robots which are used other than industry, like humanoids, like in medical field, so all these robots which are non-industrial robots falls into the category of field and service robot. Okay, and they are further categorized based on the application. So this is the most general outline or classification of the robots, industrial and field and service robots. And you have to remember that again in industrial robots there are two categories, fixed base as well as the mobile robots. If we talk about the fixed base robots, so mostly they are the manipulator arms. So we call these kind of robots as manipulator arms because its design is inspired by the human arm structure. Its design is inspired by the human arm structure. Okay, and these robots or these machines are capable of manipulating something. So with the specific tool at the end, whether you have a gripper, whether you have a welding torch, or whatever tool you attach at the end of this manipulator arm, this robot will perform the functions accordingly. Then the multifunctionality can be achieved through variety of end effectors. End effector means the toolings or the tools what we attach at the end of the robot. So this is known as the tool control point, tool center point, or TCP. Here we'll try to attach different kinds of end effectors or tools as per our application. Like here you can see a paint gun has been attached, a welding torch here, here a four-finger gripper here. So whatever attachment or end effector we will attach a robot, it will perform work accordingly. Okay, so this is the biggest capability of the fixed base manipulators. Reprogrammability, we have already talked, we can reprogram the robot. So just by changing the end effector itself, what you can achieve, that is the multi-functionality. Next, the capabilities. So mostly fixed base manipulators have two functions: specific motion of the joints, integrated tooling, and the sensors. Okay, so this is a fixed base manipulator. We have certain joints and links, and this is a fixed structure. So what we can achieve, we can achieve a certain motion pattern or a specific motion of this manipulator. Okay, so what is the application of motion, what is the intention of motion, and how we are planning that particular motion, that makes the difference. Okay, so here you can see a car assembly line where the giant size robots making assembly of the car. If you observe very carefully, then you can see that motion of these two robots is very much coordinated. The motion of these two robots is very much coordinated. Okay, it is moving in a specific manner at trying to finish that particular task. Okay, so there is a coordinated motion among the robots. This is what the role of a programmer, robot programmer. Okay, so robot programmer usually generates robot program based on certain application. So what your manipulator can do, it can follow a path, it can repeat the configuration moves, it can have teleoperation mode of control or target moves. Okay, so what we can do with the robot, we can define the motion profile. What kind of motion is required for an application, and how we can achieve or how we can govern, define that particular motion. That is the task of a robot programmer or robotics engineer. Okay, then if we see some of the application, major applications, then assembly, ultrasonic cutting, welding, These are the some of the applications for industrial robots. Okay, so what is the necessity? Whenever your task to be performed is repetitive in nature, that requires high precision and is dangerous for a human being, then that particular task is suitable for robotization. That particular task is suitable for robotization. Okay, so repetitive, high precision, and dangerous tasks nowadays are being transferred to robots or manipulators. And similarly, the other category in the industrial robots is mobile robots or AGVs, automated guided vehicles. So since in manipulators are the fixed base robots, so here we have certain movable robots. So here you can see a mobile robot platform equipped with certain wheel. This is another mobile robot which is being used for palletizing the objects. Here also you can see a mobile robot with mechanism wheel. Okay, so these kind of robots, mobile robots, are capable of locomotion. That means they can move from one place to other, and they are very much useful for supporting the autonomous operations. They are very much useful for supporting the autonomous motion. And here you can see another mobile manipulator where a fixed base manipulator is equipped on the mobile robot platform. So this gives the movability, the locomotion to that manipulator. And here in this small video, you can see a very famous mobile robot named as Spot, which is developed by the Boston Dynamics. So this is nothing but a robot dog, which is capable of performing variety of inspection tasks. So this is the categorization of the industrial robots. Now, if we go for the modeling part, how we can model the industrial robots or manipulators, then if for modeling we need to refer to the construction of the serial manipulator. If you look at the construction of the serial manipulator, it consists of certain links. Like this is the link, this is the link, and this is the link, and these links are connected by joints. These links are connected by joints. These links are connected by joints. So this is the skeleton diagram, I can say. This is the skeleton diagram of the robot. Okay, actual robot may be like this. Okay, actual robot may be like this. This is the actual robot. But for mathematical modeling, for analysis, whenever we model that robot, we'll model it like this. So this is the model. Okay, we'll have certain links, we'll have certain joints, we'll have an end effector at the end. Okay, so since these links are connected serially through joints, this fixed base manipulators are also referred as the serial manipulators. Fixed base manipulators are also treated as the serial manipulator. Then if we look at the components, as I discussed in the previous class, there will be link and there will be joint. Okay, so this is an open kinematic chain. You might remember the concepts of 4-bar chain. Okay, you might have learned in the kinematics of machine. So following in the same category, following the same categorization, this serial manipulator or fixed base robots usually refer to the open kinematic chain because one of the end is free to move. Here one of the end is free to move. So this is not a closed chain. It is an open chain. And the important components I have already told you that there will be a link and joints. There will be links and joints. So robotic manipulators are kinematically composed of links connected by joints to form a kinematic chain. So this combination of link and joint is referred as the kinematic chain. The most important part in robots, or whenever you start with the kinematic modeling part, the first thing you need to understand how we are connecting the links. So we can connect the links through joints. We can connect the links through joint. So in general, in robotics, there are two types of joints available. First one is the revolute joint, and second one is the prismatic joint. Okay, and another important feature is that these joints are having only 1 degree of freedom. These joints are having only 1 degree of freedom. So only one motion pattern, motion profile we can expect from such a joint. So this is a revolute joint. So what will be the generated motion? It will generate a rotation about this particular axis. Okay, so two links connected together via revolute joint can rotate about a common axis or axis of joint. Similarly, if you connect two links via a prismatic joint, what you can expect? You can expect a translatory motion or linear motion. So here you can observe there can be a linear motion through this joint along the axis of joint. So again, two links connected by a prismatic joint will have a linear relative motion, So what you need to remember is that these joints are having 1 degree of freedom, or 1 degree of freedom joints are preferred in industrial robots. So depending upon the way, depending upon the configuration, or depending upon the arrangement, how you are connecting these joints, a major classification of industrial robot is defined. Okay, so this figure, what you can see over here, represents the manipulator configuration based on the arrangement of joints. Let us start with the first type, that is the Cartesian type. So Cartesian type is characterized by the three prismatic joints. So in Cartesian configuration robots, there will be three prismatic joints. So this is the one joint, this is the second joint, and this is the third joint. So you'll have three linear motions. So you'll have three linear motions in Cartesian configuration type robot. So gantry crane, you might have observed, that is the best example of Cartesian configuration. Then comes the cylindrical configuration, where one prismatic joint is replaced by one revolute joint. So here you'll have two prismatic joints and one revolute joint. So what you can have? You can have a rotary motion and two linear motion. Two linear motion and one rotary motion. Similarly, next comes the polar configuration. So in polar configuration, there will be two revolute joints and one prismatic joint. And finally, it comes to the articulated or jointed arc configuration, where there will be three revolute joints, no prismatic joint. So our human arm falls into this category. This is the articulated configuration. This is the articulated configuration where all the joints are of revolute in nature. All the joints are revolute in nature. This is another configuration called SCARA. So this is a special configuration where the joints are arranged parallelly. So this joint is parallel to this joint, and this joint is parallel to this joint. So this is a special configuration called SCARA. This is very useful in assembly operation. This is very useful in for assembly operation. So this is the 3R configuration, articulated configuration, where all the joints are revolute joints. And in most of the cases, um industrial robots or manipulators falls into this particular category, that means the articulated configuration. So once you are done with the identification of the links and joint, next thing is to go for the kinematic modeling. So whenever we talk about the kinematics part, the kinematics basically deals with the motion of bodies without consideration of the forces. So this is the definition we all have learned uh, at the undergraduate level. So here also the robot kinematics also follows the same thing. But one thing we need to understand for kinematic modeling of the serial manipulator is that there will be a fixed base. Okay, so this is fixed, this cannot move, and this link, this link, this link, this link, and this link, they can move up to a certain extent based on the types of joint. But we are interested in the motion of the end effector. But we are interested in the motion of the end effector. Why we are interested? Because end effector is the part which is going to perform the necessary task for me. For example, if I have to pick up a glass of water from the table, I will move my hand and ultimately my palm will grasp the glass of water. Similarly, here also, whatever be the motion profile of these joints or these links, ultimately we are interested in the motion profile or the motion of the end effector. Motion of the end effector. So this motion is quite important for us. But since it is a serial structure, this is fixed at this particular position. Okay, and this is moving freely in space like this. What we try to do, we try to define this motion with respect to fixed reference frame, with respect to a fixed reference frame. So this fixed base serve as a reference frame for defining this motion. This fixed base serves as a reference frame or as an origin for defining this motion. So suppose this xy coordinate is defined over here. This xy is nothing but this is the x position from the origin. This is origin O, and this will be the y position. This will be the y position. Okay, so this is x and this is y. Whatever coordinate you can see over here, x, y, okay, those coordinates are defined with respect to this origin O, defined with respect to this origin O. Okay, I hope this is clear. So in kinematics, we try to estimate or we try to predict or we try to define this motion interaction with the environment. So that is all about the kinematics part. Okay, but before going to define the kinematic equation or understanding the kinematics further, we need to understand the two things. First thing is the position that I have already described, that this is the position coordinate your robot has to reach, and what will be the orientation. So orientation refers to a particular combination or set of angles to which an object can be grasped or an object can be approached for performing a particular task. Okay, so what are the different ways of defining position and orientation in that could play a crucial role in robot kinematics, because there are several ways to define these entities. So usually what is the standard practice? We assign one or more coordinate frame at each place. So this is my fixed frame. Okay, now I will define the next frame over here. Next frame I'll define over here. Next frame I'll define over here, like this. And with respect to, and I'll try to analyze the motion of the frame can be an then there is a frame x1 y1 3c over here. Frame number 1 and frame all the motion, all these to the base frame. Okay, so this is the concept, and for that thing, for that representation, we'll use certain mathematical tools. We'll use certain mathematical. You can define the position of a point or vector in 3 space is defined. So you can see there are two frames, one capital X, Y, Z you can see, which is referred as the G frame, that is nothing but the ground frame. And there is a point P. There is a point P in 3D space. Okay. We have defined another frame that is small X, Y, Z. So this is the same or second reference frame. So this origin or frame that. Okay, so the same point P can be represented in two different frames in two different ways. So when you represent this point P with respect to this origin, with respect to this origin, the coordinate of that point is written as XYZ, that is capital XYZ when you are representing this particular point P in the ground reference frame with respect to this origin. So this will be the coordinate XYZ. Similarly, when you are defining this point locally in the local or the body reference frame, then what will be the coordinates? In that case, you need to take the origin as this and you need to define this vector. Sorry, you need to define this vector. Okay, so in that case, what will be the coordinates of same point P in the local reference frame? It will be X, Y, and Z, that is the small case letter. Now there are techniques available to correlate these two frames. That means you can analyze what is the position of or what is the movement of this body frame with respect to this ground frame, and in the same fashion, in the same manner, what will change? The description of point P will change in either of the frame. The description of point will change either of the frame, that is the ground frame as well as the body frame. So this particular operation is referred as mapping. This particular operation is referred as mapping when you try to analyze motion of one frame with respect to other frame. So there are three ways to map. First one is the rotation. Second one is the translation. And third one is the rotation plus translation. Rotation plus translation. That means this frame to this body frame may be rotated with respect to ground frame. This second frame may be translated with respect to first frame, or This second frame may have both rotation and translation with respect to the first frame. First frame or one reference frame we need to fix, and we can analyze the situation, we can analyze the condition of the second frame through the mapping operation, okay. Then comes the orientation. So orientation usually defines the way how the end effector or is oriented towards an object. So this is related with the angle. This is related with the angle. So here you can see a cubical rectangular block at a certain position. So there are three axes x, y, z. There are three axes x, y, z. When you rotate this particular block with respect to different axes, it may have different orientation. For example, if you rotate it about x axis, this will go up. If you rotate it about y-axis, this side may go down. If you rotate it about z-axis, it will rotate like this. So depending upon how the rotation is made, what is the amount of rotation, your object may have different orientation. And what is the easiest way of defining rotation? To use the rotation matrices. So these are the three rotation matrices. This rotation matrix describes the rotation about z-axis, this rotation matrix describes the rotation about y-axis, and this matrix describes the rotation about x-axis. So there may be several combinations, there may be several rotations, okay. So that we can compute or that we can analyze using this rotation matrices. There are some other forms also of rotation for rotation representation, like we may have Euler angles, we may have roll pitch yaw representation, okay. We may have roll pitch yaw representation, okay. But all comes from this fundamental, that is rotation, how the rotation has taken place, whatever be the form, whether you are using maybe the Euler angles, maybe the roll pitch yaw. You cannot neglect the necessity of these rotation matrices, because the computation goes from here. First you need to compute the rotation matrices, then only you will be able to compute the other forms of representation like Euler angle or roll pitch yaw angle. So first thing for kinematic modeling is the position and orientation representation. This must be clearly understood, okay. So then comes the problem of kinematics. What are the two cases? There may be forward kinematics and there may be inverse kinematic problem. So what is happening, since this is a fixed base robot, so what we have at our hand, we have say three joints. We have joint number 1, joint number 2, joint number 3. These are the three joints. And in what particular fact we are interested in? We are interested in the motion of this end effector. We are interested in the motion of this end effector. Plus, try to understand this end effector is moving in a 3D coordinate system. This is a Cartesian coordinate or 3D coordinate, or the space in which we live. This is moving in this particular space, Cartesian space, 3D Cartesian space. And what are the inputs we are giving? We are giving the, as an input, we are providing some joint angle values to these joints. Say Q1, theta 1 may be 30 degree. This may be 40 degree. This may be 50 degree, likewise. So what we are giving the joint angles, and what we are trying to achieve, we are trying to achieve the motion in the 3D coordinate system or the world coordinate system, Cartesian coordinate system. So when these joint angles are given, and effector position and orientation, that particular problem is referred as the forward kinematics or direct kinematics. So here, by using this set of joint variables, we will be estimating the end effector position and orientation. We'll be estimating the end effector position and orientation. Now consider the reverse case. This end effector position is given to you, that is x, y, theta. This particular parameter is given to you, and what we are trying to find, what will be the equivalent values of the joint variables q1, q2, q3 and q4. q1, q2, q3 and q4. Then this particular problem is referred as the inverse kinematics. This particular problem is referred as the invert kinematics. So forward kinematics problem is a straightforward problem. There is a well defined procedure to establish the forward kinematic model. Okay, so this is a straightforward and simple problem where you will have certain formulas, certain procedures, certain algorithms that you can use to estimate the forward kinematic model. But for inverse kinematics, the solution is not so easy. It is most complex problem. It is most complex part of the kinematics, inverse kinematics. Why? Because there may be several combination existing. For a given position and orientation, and there might not be any solution for some configuration. So everything we need to check while analyzing the inverse kinematic solution. So let us see quickly what are the steps for the forward kinematic model or forward kinematic modeling. So here you will be given a set of joint angles and we'll be estimating the end effectors position and orientation. So this is the straightforward problem statement. Then what are the steps? So first step is to assign the frame, because these frames, what you can see over here, the coordinate frames, they cannot be assigned simply. There exists an algorithm or there exists a procedure which we need to follow. So that algorithm is known as the Denevit-Hartenberg or DH algorithm. So we have to use this particular algorithm for frame assignment, because different arrangement of joints, prismatic or revolute, and how they are connected may result in different configuration. Therefore, we have to follow this standard notation. We have to follow the standard procedure of Denevit-Hartenberg algorithm to assign frames to a manipulator. Afterward, you have assigned the frames. The next task is to estimate the DH parameters. So what are the DH parameters? There exist 4 parameters: A, alpha, D, and theta. So these 4 parameters can be taken as a signature of any robot. If you know these 4 parameters, A, alpha, D, and theta for a robot, you can perform the entire kinematic, dynamic, and all sort of modeling. So this is the basic requirement. So this A is referred as the link length, alpha is referred as the link twist, D is referred as joint offset, and theta is referred as the joint variable. So after frame assignment, using the convention given in the DH algorithm, what we can do, we can estimate the DH parameters and form a table like this. So this is for an n joint robot. There will be n parameters. Okay. So this is the first step. Then second thing is to write the transformation matrices. Once you have defined these DH parameters. Using these DH parameters, there exists a set of convention which you can use to define the transformation matrix for each link. So this transformation matrix is representing the position and orientation of the previous frame with respect to next frame. So here you can see this is I minus 1 Ti. So this is representing the position and orientation of frame I with respect to I minus 1. Okay, so likewise you need to write the transformation matrix for all the things, all the joints, links. So if it is an n jointed robot, n degree of freedom robot, you will have n such matrices. And finally, to form the forward kinematic equation. So once you are done with, you have defined these matrices, you can simply multiply those matrices in a straightforward manner to get the forward kinematic equation. Okay, so here an example of 2 degree of freedom robot is shown. So this is a 2 degree of freedom robot, okay, having 2 joints and 2 links. So this is the DH parameter for the robot, L1, L2, 0, 0, theta 1 and theta 2, only 2 variables. Okay, so likewise for 2 frames, you'll define 2 matrices, 0 T1 and 1 T2. 0 T1 and 1 T2. These are the 2 matrices that you define, and finally you will multiply these 2 matrices in following order, 0 T1 into 1 T2. So that will give you 0 T2. That means this point is now represented with respect to this fixed base. So this 0 T2 means the position and orientation of frame 2 with respect to frame 0. So using this particular expression, we are able to define the position and orientation of the end effector with respect to fixed space. Okay, so this is applicable for n degree of freedom robot also. So you may have 6, 7, 5, 4 degree of freedom robot. So accordingly, you need to form the transformation matrices for the given robot, and then you need to multiply it together to form the forward kinematic equation. So this is the procedure for forward kinematic modeling. And similarly for inverse kinematic modeling, as I told you that it is the most complex part, because we'll be given with this particular expression, that is the position and orientation at a particular instant will be given. And what we need to find, we need to find the theta 1 and theta 2 or the joint variable values. So why I am saying that this is complex, because look at this particular position. This is a particular position for end effector where the coordinate is x2 and y2. So this x2 y2 configuration, the robot can reach in 2 configuration. Either joint 1 will be like this, and link 1 will be like this, and link 2 will be like this. This is the first configuration. Or what will be the alternate way? Alternate will be this red configuration. So you can see this and this. These configurations again lead to the same position and orientation. Okay, the second configuration also leads to the same position and orientation. So there exist multiple solutions. There exist multiple solution, or there exists no solution. And for solving the inverse kinematic problem, we have to deal with the non-linear algebraic equations, which may be very difficult to solve at times. Okay, so therefore only for a limited set of robots there exists the closed form or analytical solution exists. Only for a limited set of robots closed form inverse kinematic solution exists. For rest of the cases, what is the option we have? We have to go with the iterative methods. Okay, so this is just a primary intro about inverse kinematics. So this is the problem statement what we have. This is given, this position and orientation information at a particular instant is given to us. What is the first step? Again, to follow the forward kinematics and compute this particular expression. This is given, this is given, and this will again compute as to solve the inverse kinematics. So again you need to get the transformation matrices and forward kinematic equation like this, and then what you can do, you can compare these two expressions. You can compare this 0 T3 with the given set of matrix. Sorry. And after doing a lot of stuff, after doing a lot of mathematics, equation solving, you can come up with the values of theta 1, theta 2, and theta 3. So here you can see that for this particular example, theta 2 is not uniquely defined. Theta 2 is not uniquely defined. We are getting the value of theta 2 in combination, that is theta 2 plus theta 3. We need to solve this particular equation to get the theta 2. So there exists complexity in the inverse kinematic solution, okay, that you need to analyze very carefully. Okay, so this is all about the forward and inverse kinematic part. And at the last, I would like to just give you a brief introduction to Robo Analyzer tool. So in order to learn these fundamental concepts, that means the DH parameter, the forward kinematic modeling, frame assignment, mapping, you can utilize a free software tool called Robo Analyzer. You can utilize a free software tool called Robo Analyzer. So this is a 3D model based software that can be used to learn the robotics concepts. So whatever things we discussed in this talk or in this lecture, you can easily get, you can easily visualize those things in the software Robo Analyzer. It is developed by IIT Delhi and it is freely available for the educational use. So every student can download this particular software and you can utilize to learn the robotics concept. Okay, and one best part is that you need not to install this robot. You can simply download the zip file, then there will be one executable file. You can use that thing to learn. I'll just show you. Is it visible, sir?
We are still waiting for the screen. Yes, sir. It's visible now.
Yeah. So this is just a representation in Robo Analyzer. So this is a 2 degree of freedom robot. We can see the 2 revolute joints over here, and here is the table of DH parameters. Okay. And what we can do, we can perform the forward kinematic analysis, and we can see the motion and what are the changes happening over here in the matrices, in the trajectories. Everything we can track. So this is the end effector configuration you can see at the bottom. Okay, and variety of robots from 1 degree of freedom up to 7 degree of freedom are available over here, as well as some real industrial robots are available. Okay, so like here KUKA KR 6 robot is there. So whatever the concepts, the fundamental concepts are required, like frame assignment, how the transformation matrix works, or how the position and orientation are computed for an industrial robot, that can be easily visualized through this particular software. So I request all the students to please do use this software tool so that you can understand the concepts better. Okay, so at this point I would like to stop. And I would like to thank one and all for your patient listening. Thank you. And if you have any queries, you can ask.
Thank you, Abhishek sir.
Okay, so at this point, I would like to stop.
Thank you, Abhishek sir, for sparing your valuable time. Please clarify a few queries from the student side. Abhishek sir, please on the video.
Sure, sir. Yes, sir.
Please on the video.
Yes, sir. Yes, sir.
Students, those who want to have the clarifications, please come forward. Please come nearer to the camera. Hello, Mr. Nitish. Okay. Okay, Mr. Nitish, please put your query.
He's not audible, sir.
Nitish, please check your audio connection. Or Nitish, otherwise you can connect from your mobile phone.
Sir?
Abhishek sir,
Yes, sir.
Morning, sir.
uh,
I am B. Nitish
Yeah,
Kumar.
please go ahead.
Nitish, please speak loudly.
Please go ahead with your question, Nitish.
Sorry. Good afternoon, sir.
Please go ahead with your question.
Actually, my question regarding the application in the point of end effector, can we replace the turret? Because if we use the end effector, it has only one point of application. If it was replaced by a turret, we can perform a multiple functions at a time. Is it possible by using mechanisms?
Replaced by what? And effector you want to replace with what? Hello,
So, actually, same mechanism that you are
am I audible?
with CNC.
I'm not understanding your question. You want to replace end effector with what? What is the one thing that you'll attach at the
Sir, I am having the doubt.
PCB?
I am having the doubt regarding the mechanism only, sir. Is it possible to build that type of mechanism uh, by replacing the end effector with the turret?
Correct. Yes, mechanism design is certainly possible, but whatever concept you may have, without visualizing that thing, it will be difficult to comment what exactly you are thinking and what exactly I am understanding. So, if you have something on paper, then we can give, because for mechanism design, it's an open field where uh, you can have mechanisms as per your requirement. You can design them, you can synthesize, you can create new applications. So modifications are quite possible. Modifications are quite possible, but again, you have to look into the problem statement, what exactly you are trying to achieve and what sort of modifications you are trying to achieve. Getting my point?
Yes, sir. Thank you.
Any other questions?
Morning, sir.
Yeah, please go ahead with your question.
Sir, are there any applications regarding inverse kinematics, sir?
Application of what?
Inverse kinematics.
Inverse kind of application means what? What sort of application? With inverse kinematics, not possible to plan any of application robot. So inverse kinematics is a must. Inverse kinematics is a must for industrial or any sort of robot, because whatever task we are trying to achieve in the with the robot, the task is usually defined in the coordinate 3D coordinate system. Like you are trying to weld two plates, you are trying to paint something, so paint path or the weld path or the object coordinates you will be defining in the 3D coordinate system. And for operating the robot, what you need joint angles. So anyway, through any means and anyhow, you have to perform inverse kinematics. So you cannot skip the inverse kinematics part.
Students, any more queries? Hello? Hello, from the student side, any more? Thank you very much, Dr. Abhishek Jha sir, for sparing your valuable time. If any more are there, we will have conversation with you in the next series. Students,
Sure,
sir has,
sure.
sir, students, please keep your queries. I will share the mail ID of sir, because sir has meeting at 12 o'clock. Already it is 4 minutes late. If any more queries are there, sir will answer through mail. Thank you very much, sir. Dr.
Thank you,
Abhishek
sir.
sir, for
Thank you very
sparing our
much, sir.
time.
Thank you, sir.